Hello everyone, welcome back to MLC. This is episode 9. In today's episode, we're going to talk about how we're going to do high-level computational graph optimization. To recap a bit, in previous lectures, we learned a lot about different MLC processes that allows us to transform among different tensor functions. In particular, we have learned about how can we take primitive tensor operators represented in an abstraction called tensor and how can we transform those programs so that we can get a program that are specialized to the hardware of interest. And along with that, we also learned about this high-level computational graph abstraction, right? That allows us to represent the high-level computations. And there are a lot of transformations we can also do on these high-level computational graphs along with this primitive tensor function. For example, in this particular figure, one thing we can do is we can take two primitive tensor operators in here and try to run them and convert them into a single computational graph node represented by fusing these two things together. And another thing we are doing actually in this particular figure is that we are trying to take this linear value and expand a corresponding lower level loop level representation so that we will be able to run transformation that optimize this particular loop program further. Most of the MLC process can be viewed as transformations among those tensor functions. And today we're going to dive deeper on, right now we are doing it visually. And let's start to think about how can we write a program to do this type of high-level computational graph transformations. Okay, so to begin with, let's start with a simple example. So in here we are trying to evaluate a specific kind of tensor programs called relax, and this program represents a simple operation, right? It takes in x and y and try to compute y plus x times y. Okay. And we are doing this through two operations in here. First of all, we're going to multiply x and y. And then we're going to add the result back onto y in this case. This common two sequential pattern is a very common pattern appearing in most of the compilations. Actually, it's called fuse multiply add. So in this case, although we are doing it in two steps, usually in a lot of cases, they are accelerated primitives that allows us to do it in one step. In this particular example, however, at a high level, tensor computation is not necessarily useful to represent the multiply add using a fuse version. But we are only using this example to demonstrate what are necessary APIs we can use to transform this high level computational graph code. Okay, so before we start to run some of the transformations, let's start to look at what's under the hood what are the things that are under the hood that backs this particular relax program in this Python AST form. So one thing we can do is we can try to get out the relax function here and look at its type. You'll find that this particular relax function contains a type of, of course, relax function. And it contains several fields. So it will have a parameter field that represents effectively the two parameters that we have in here. And they have a body field that represents a function body. In this case, the function body is of type sequence expression. And then the sequence expression will contain a list of binding blocks that correspond to this set of bindings we have previously. And in this case, we only have one binding block, and this particular binding block corresponds to there's two sequence of operations that contains multiply and add. And we can also try to print out the bindings, which contains two var bindings, and we look at particular one var binding. It contains a variable that shows what are that shows the left hand side of a value and the value that correspond to the right hand of the value that you're binding to. Of course, we are doing a quick whirlwind tour of the data structures, right? It can feel a bit confusing on when you directly go and run the code. So next, let's try to look at these two data structures from, and on the left hand side is the original original Python TVM script code, and on the right hand side is a visualization of a corresponding data structure that we just walked through over. So in this case, you can find that this particular main function corresponds to a data structure called relax.function. So I'm going through the code example again, except that we're doing in this visualization, right? So it contains a two parameter field, that's x and y, which correspond to these two parts. And then the particular body of the function is what we call a sequence expression. So a sequence expression will contain a sequence of binding blocks. In this particular case, we only have like one data flow block. Actually, that's the most commonly that's the most common case in a lot of computational graph optimizations. In other cases, if we have like side effects and multiple data flow blocks, we could have a sequence expression that contains multiple data flow blocks. So a sequence expression have a field called blocks that lists all the blocks that we have. And in this particular case, we have one block, which is a data flow block in here. And data flow block, recall that data flow block effectively represents a computational graph where each of the computational graph node within the data flow block contains only side effect free computations, so that we will be able to view it as a directly acyclic graph, just like a normal computational graph. And then within the data flow graph, we have a list of bindings in here, and each binding corresponds to one line of the left-hand side that that performs in here multiply and add. Okay, so if you look at the visualization on the right, it roughly represents what the overall data structure looks like to support the TVM script code on the left-hand side. And finally, for each of the var binding, they have a left-hand side and right-hand side. So the left-hand side is a variable, a field in here, and right-hand side contains a value field that corresponds to the value that we're binding to. And in this particular case, this value is a core node, just like we listed out in here. So effectively, it's a core node with operation field that runs relax.multiply. And then it contains two inputs, x and y. So this variable corresponds to x, and this variable corresponds to y in this case. Okay. So one of the things that we want to ask is, can we take this computational graph on the left-hand side and trying to fuse the multiply and add operation together? Because we know that we might be able to get a more accelerated version, or for other reasons we simply want to fuse it together to demonstrate this graph transformation. So effectively, what we want is to be able to take these two variable bindings and turn them into a new variable binding that effectively performs multiply and add. Okay, so there are different ways that we can do it. Of course, one way we can do it is we can recursively visit the data structure that we have that represents this high-level computational graphs, and then we're going to reconstruct another relax function, right, that corresponds to the new AST that makes the two things fusing together. This is of course doable because all the data structures that we have in here are available in Python. We'll be able to build. Actually, it's an interesting exercise if you want to go ahead and do it from scratch. So another thing that we can do, and this is what we're going to do now, is that we're going to use some additional data structure and the toolings that help us to simplify this process. And in particular, we're going to use a pattern called visitor pattern to do this rewriting. So here's a particular code example that shows how can we do this FMA rewrite using a visitor pattern. And in here, relax.py expert mutator is a mutator class that helps us to do rewriting. Okay. So what visitor pattern tries to do is that it will try to go ahead and recursively run and visit this abstract syntax tree on the right-hand side. And for each kind of the node, for example, in this case, this is a sequence expert, this data flow block, it's var binding, and in this case, this is a call node. They will call what we call visit function that allows us to be able to visit this node. And this particular case is a mutator. So the behavior of mutator is that it's going to do call visit that gives you an original node, and you can try to return a new node that you want to use to replace this particular node. For example, in this case, when I call visit of relax.add, I can try to say I'm going to return something like relax.multiply, and then the return new node will get replaced in this location, and you will get something that is gv equals relax.multiply. Okay, so let's take a look at this code logic in here on how we're going to implement this fused multiply add operations. So as a first step, what we're going to do is we're going to call expert visit post order. So this is calling the parent's definition of visit call effectively, that tries to first of all do some of the helper functions to remap some of the variables if some of my input have already been rewritten. So it's a common thing that we are doing. And after we call this visit post order, we are going to get a call. And one of the things we're going to do is we're going to detect whether or not there's a pattern that we're interested in here. And if it matches the pattern we're interested in, we're going to try to replace the call. Otherwise, we're going to return the original call. Okay. So in here, what we're going to do is we're going to get three operations in here: add op, multiply op, and EY FMA op. These operations correspond to the primitive operations that we have in TVM, and you will be able to pattern match this. We'll be able to use those to pattern match the particular code that we're interested in. So first of all, we're going to check the current call. And because we're interested in multiply add pattern, right? So effectively we're interested in something like add LV0, some result, and you want to say LV0 equals multiply actually before add in here, right? So first we're going to check if the current node is an add node. If not, of course, the pattern match fails, so we directly return the call value. The second thing we're going to do is, assuming that we already have add in here, and we have add in here of two inputs, we're going to check the first input, the value of first input, right? So in this case, the relax program usually sits in a form called a normal form, which means that every input to the teacher function is a specific variable in here. So if you look at our original program, you'll find that effectively this is LV0. So once we detect this, I want to know like what does LV0 correspond to. So what we can do is we can do a lookup binding that tries to give us whether or not if it's being binded in a previous variable bindings, it will give us the value of that binding value. Of course, in certain cases, the particular var can correspond to the parameter of the function. In this case, does not correspond to an existing binding in current data flow block. And in this case, the value will return none. Okay, so in this case, we are trying to look up bindings, and we're going to try if this particular binding corresponds to another core. Okay, if it's corresponding to another core, and if this value is multiplied, then of course we have a successful pattern. But if if neither of the conditions are satisfied, we will need to return the original call, which means that my pattern matching is not successful at this point. And once we have done this, and at this point all the pattern matching is successful, what we can do is we can go and construct another core that contains the new FMA op, and it contains two of arguments, value.arg0, value.arg1, that correspond to the two inputs of the multiply, and then call arc1 correspond to the second input of the add. Once we construct it, the new call, we can return it as a replacement of that of this visit call operation. Okay, so effectively, the ideal visitor pattern is that we're going to specify for each kind of data structures. We're going to look at certain patterns, and we're going to say that whether or not we are interested in replacing this particular value or particular node with another value of interest. So we'll go ahead and run this. You'll find that so in here, what I'm going to do is I'm going to instantiate a version of this mutator and call visit expert on a function that we're interested in. And what it's going to do is that this visit expert is going to recursively traverse that particular function shown in the AST that we just walked through in here, and tries to look into each of a side, and for each of the calls, we're going to invoke that function. In that particular case, when we invoke visit call on this node, it's a pattern that's matched, right? So effectively, it's going to return the FMA add operation. It's also going to invoke visit call on this particular node here. And in this case, it's going to multiply operation. So remember that then this condition wouldn't satisfy, it's going to return the original call. And as a result, we are not going to touch that particular binding values, even though we have called visit call on that binding value. So if you look at the end result, you'll find that the second line get replaced by EY's FMA XYY, which is a desirable result that we're interested in. One thing you'll notice is that actually we still keep the first line. Right? In this case, actually this first line is what we call dat code, because it's a local variable binding within a data flow block that's not being referenced anywhere. So actually it's safe to delete this particular operations, and we can do that by what we call a function called remove all unused. And if we do that, you can find that the final operation contains the EY's FMA that takes x and y, multiply them, and add them to y. And this is the first attempt that for us to write a computational graph transformation based on this Python visitor pattern. Okay, so far we have get a taste of how can we use the visitor pattern to manipulate this abstract syntax tree using Relax, and trying to allow us to be able to take two computation operations and fuse them together as into a new node. Let's start to try some other possible computational graph transformations that are closer to a real world setting. So in this particular case, let's first reuse the models that we used in past few lectures, the fashion MNIST model. Remember that this particular model contains several layers, right? It contains two fully connect layers in this case, and a biased add layer along with a ReLU layer in between. And so we are going to use, in this case, we are going to use the block builder API to build this. And once we create the model, here's a high-level Relax code that is used to represent this particular end-to-end model. Also, you might notice is that in this case, we are again using the high-level computation operations as opposed to using emit TE, right? That directly give us the lower-level tensor function calls. Actually, the computational graph optimizations can work on both settings. And to make things more general, actually we encourage writing some of the computational graph transformations based on analysis of the tensor functions. In those cases, actually analyzing tensor functions and doing transformation model can be more general than those high-level operations. For this particular lecture, we are trying to make things a bit more simplified. So looking at higher-level computational graph operations, it's simpler because you can directly look at the primitive operation and pattern match on it. So there are pros and cons, but the techniques that we are teaching here actually can be applicable to both cases. So one of the things we are going to do is we're going to try to do what we call fusion operation. In this case, we are interested in recognize a dense and add pattern. So imagine that we have input x, w, then you have add that takes a bias turn. We're interested in recognizing this entire computational graph and try to fusion onto a single code block in here. And this optimization is commonly used in a lot of the higher level computational graph optimization. As a matter of fact, fusion is likely going to be the most frequent topic besides like layout writing and memory planning. And it's one of the most commonly used computational graph optimizations for high level computation. So let's try to do that. And in this case, what we are interested in is we want to be able to recognize a pattern that contains dense and add. We want to put them together as a single function. So we're also going to use a similar pi-x permutator in here. And the idea is we want to go ahead and detect a dense operation and add operation. And then we want to be able to, in this case, we will not create a new primitive operation called dense add, because if we start to try to create the primitive operations for all the possible combinations of fuse operator, there are going to be exponential amount of possibilities, right? So instead, what we're going to do is we're going to just detect the dense and add and try to isolate them onto another subfunction that marks effectively, hey, I want to fuse those two operations together. So if you are a bit confused of what it means, let's go ahead and go through the code. I'm going to show you what's the end result, and you will understand what we mean exactly. So let's go ahead and first run this code and see the end result before we come back to the implementation of the code. Effectively, after we run this code, our end goal is to produce this program. In fact, you will find that this program contains two subfunctions, fuse dense add 0 and fuse dense add 1. Within each of the subfunctions, it contains two dense and add operations, except that the input shape of each of the function is specialized to the shape of the particular fuse dense add pattern. So effectively, you can find the transformation we're doing here is we're taking the original computational graph, we're detecting the dense and add operations, and we're trying to turn them into another function, right, that we can call into. So these two subfunctions naturally marks the boundary of the fusion that we are interested in. Okay. So let's come back to implementation of this. The implementation is relatively similar to what we had before. First of all, we are going to have, in this particular case, the dense add filter will input an IR module. That's the IR module that we're originally interested in. Give us a transform function that will return a new IR module that's in a transformed version. So in here, what we're going to do is we're going to iterate over original IR modules, find out all the possible relax functions. In this case, for a relax function that contains a primitive attribute, it's a function that's already being grouped as subfunction. We want to skip them. We're only interested in the functions that are non-primitive. And then what we're going to do is for each of the functions, we're going to call visit expert to update that particular function, remove all the unnecessary local variables that are not being used within the Airflow block after updating. And then we're going to update this particular function. In this case, each of the mutator contains an internal block builder that allows us to use them to build a new functions that we are interested in, and based on the original IR module. And in this case, we're going to update the original function with the updated version. Finally, we're going to use the builder.get that's going to give us the IR module after the update. Okay. So here's the transform code, and let's start to look at visit call code. In this case, in the visit call code, we are going to try to detect a pattern that's called dense and add. So the first thing we are going to do is we're going to define a generic function called match core. Effectively, it detects whether a node is a relaxed core node and if the operator matches together. Okay. So let's start to do pattern matching because we're trying to detect a dense and add operation. The first thing we're going to do is we're going to first detect add operation to say, this if there's something that's available of add, and if not, of course, we're going to return original value because the pattern match failed. If we match the first level, the second thing we're going to do is we're going to look up the bindings of the first add operations and check if that's a dense operation. Okay. And if the value is dense operation, it constitutes a correct match. Otherwise, it's not effectively, we're going to return the original call, which means that we are not going to modify this particular call node. Okay, once we finish the matching, what we can do is we can extract out all the corresponding values in here. And in this case, because we are not going to create a new primitive function call, so it's slightly more complicated. We need to create a different functions, right? That we're going to add back to our original set of functions in here. So first of all, we're going to create a new builder to build that new function. And we're going to assign a name, and we're going to use a counter to record, what is the set of totally dense add functions we have so far. And then this particular new function contains two operations. First of all, we're going to, it contains three parameters, w and x, w, and b. We're going to do a dense and add operation, and that's my final output. Once I get that particular function, I will be able to take that function, and I'm also going to attach additional attribute called primitive that marks that, hey, this is a relaxed function that corresponds to a fused group, right, in here. And this is just a convention that we're using to mark the corresponding fused function. And then we're going to add this function to our current IR module that's being built. And in this case, after we add it, it will give you a global variable that we can use to referring to that particular added function. So after we add this function, we can do relax.call to call into that global variable, and this will construct a new call node, effectively that calls on to that corresponding fused dense add operation here. So this is the original mutator that I'm creating, and the second thing we're doing is we're going to wrap it as a pass. So here pass is just another wrapper data structure that we create that allows us to be able to that allows us to create a wrapper that represents transformations among IR module and IR modules. So in here we're just taking a module and we're going to call the dense and future.transform that gives us the transform result. So once we have this parse, one thing we can do is we can take an original module and then run it through the parse constructor that gets the parse, and then give us the MOP fuse, which is the final return output. If you look at the output again, you can find that gives you a fuse dense add operation here. One thing I want to mention is that what we're doing here is not so typical. If you look at other machine learning frameworks, most of the cases when people are doing fusion, people are simply detecting patterns, and we're not creating those sub-functions. Instead, you would directly replace it with something like relax.fuse dense add operation that contains a special implementation. The reason why we are choosing to create a sub-function in here is that in a lot of cases we're interested in a lot of generic fusion patterns. For example, not only we're interested in fusing dense and add, we're also interested in fusing dense and then ReLU, dense and ReLU and multiply and so on. So there are exponential amount of possible opportunities that we can do in a lot of fusion passes. In reality, the most powerful fusion passes will also try to make use of these opportunities. For example, the matured fuser will try to fuse all the possible element-wise operations onto a dense operation, regardless of what kind of computations in one. So in order to perform that, we can no longer introduce a specific type of primitive operations for each type of fuse operator. And this particular fuse dense add subfunctions help us to represent effectively here's a fusion group while containing all the necessary information for a low-level code generator and future optimizations to be able to leverage and generate a fuse operation. So that's why we are following this, different convention that's actually more advanced and help us to be able to represent more possible fusion patterns in the future. Okay, so far we have done the first transformation that takes the original function and we are fusing the dense and add operation together. As a second step, in order for us to really create something that runs on the hardware, we still need to be able to map those operations like dense, not dense add here, but at least add, dense, and relu. Those are all high-level primitive operations, so I still need to map them onto something that's runnable on the hardware. And in order to map them something that's runnable, remember that for primitive tensor functions, there are two approaches. So we can either map them onto the library that correspond to an opaque function call in the environment, or we can map them to tensor-ai function that we can further do transformations, thread bindings, and trying to even do automatic program transformation to match them on the corresponding hardware of interest. So in this case, let's try to map those primitive tensor functions onto tensor-ai calls. And one interesting thing is that we can also treat that as a computational graph optimization. In this case, we are just going to recursively visit all the calls that correspond to high-level primitive operations. We're going to translate them onto a lower level, on a lower level call onto a tensor-ai function. So here's the implementation of this. If you look closely, you'll find it looks very similar to the original importer that we implemented in the framework integration section. Because in that importer effectively is traversing over a computational graph from PyTorch and effectively map them onto a computational graph that contains tensor expression operation. In this case, we're just going to traversing a computational graph represented in relax, but with high-level operations, we're going to traverse and remap them onto the corresponding low-level operations or tensor level operations. So this is a parse that this is a mutator that we're going to write. Effectively, we are going to do visit call, and for each of our calls, we are going to look up what we call an operator map that specifies for each kind of operator how we are going to translate that call. Okay, so this is something that's not yet to be defined, and we're going to look at definitions down here below. And then this transform function is kind of similar. It's just going to recursively visit each of the functions and going to update the corresponding value with the new global variable in here. Okay. And then here are the mapping functions that we have. So for each of our calls, what we're going to do is we're going to return what we call call TE. So this is slightly similar to emit TE, except that in this case, call TE is not going to return a new binding. It's just going to create a tensor function and return a call node to that. This is because we are transforming a call node that's already a binding available. So I just do call TE here. And so in here, X and Y are the input arguments. What we're going to do is we're going to call TE top_i.dance. This is the tensor expression implementation. And the first argument is a block builder. In this case, the particular visitor have a block builder attached to it that allows us to use to construct any new any new additional functions that we might want to add to the current module during transformation. Okay, and once we do call TE under the hood, what it's doing is that the block builder is going to create a new tensor function using the tensor expression, and then generate a call tier node that calls onto that tensor function. So similarly, for add, we're just going to call the top_i.add, and relu, we're going to call t.top_i relu. This is the corresponding lower level mapping function that we can we can customize and send onto this lower level tensor translator. Okay, and again, we are going to wrap it as a pass that allows us to effectively, do things in a more unified way. A TVM having structure to do things like train passes together and also introspect during passes and so on. So it's just another level of wrapping to make it more standard. And then we can go ahead and run it. Right? We can create this pass that actually leverages this operator map here and place in the input originally fused functions in high level primitive ops, and we're going to turn them on to a low level tensor function call. Let's try this. After run it, you will find that we still have those fused dense add operations, and the ReLU operation is already turned into a ReLU operation in here that correspond to let's say ReLU operation in here, right? So that corresponds to tensor functions. And then for those fused dense add, you'll find that within fused dense add, for example, in here, it also turns those high-level primitive functions into calls onto the lower-level tensor function. In this case, dense and add operations, right? Each of them are being implemented separately. For example, this is an add operation in here, and we also have implementation like dense operations in here in tensor. But one thing we notice is that, ideally, when we want to really fuse things together, we really want to be able to perform this dense and add operation in a single shot, as opposed to, still doing it in a group subfunction where we are calling two tensor functions separately, right? So we really want to have a final function that, fuses those two things together. So the TVM provides an additional path that turns those fused dense add operation that contains two call tiers onto a single tensor function. And that path is slightly more complicated, so we are not going to implement by ourselves. We're going to invoke this path called fuse TIR. And after this, what you'll find is that the original fuse dense add operation in the relax function disappears. And the only thing that's left here is two call tier function to fuse dense add 1, fuse dense add 0, and fuse dense add 1. And the fuse dense add 0 and fuse dense add 1 will correspond to a tensor function that fuses the original two call tier function together. So effectively, you can view this original fuse dense add function as the input specification to the fuser, or hey, I really want to fuse those two call tier function together. Here's how I group them in an organic way. And then fuse tier is going to take that fusion decisions and try to generate a low-level function that stitches things together. So in some sense, we are separating the decision of what to fuse and the action of actually fusing them. So previously, we are trying to writing passes to provide decisions on what to fuse by creating those subfunction that groups things together. Then fuse tier is going to create a tensor function that puts things together in a fused function. Of course, in order to generate the most efficient fused code, we still need to be able to take those code blocks and run additional transformations, like inlining the addition function, for example, back onto the matrix multiplication operations after we compute some of the blocks of computations. We can do that using automatic scheduling mechanisms that we introduced in the past few lectures. Or if you're interested, you can go ahead and take out the function and manually transform them as you will. So we're not going to go through this, but this basic flow kind of demonstrates, actually a huge spectrum of life in terms of what things can happen during a computational graph optimization phase and machine learning compilation phase. So after we get this transformed fuse tier function, in the next step, we're going to go ahead and build and run this function. And so we're going to use the fashion MNIST models. And here's a bag, right? And we're going to run it through this particular function by putting in the final module setting here, and it predicts back as expected. So in some sense, this is effective MLC process that start from high-level module creation, transform it using operator fusions. Then we are going to lower that onto a low-level tensor function, run fused here to fuse all those low-level fuse operator onto really a single operator. And then you will get a runnable program. So today we are really experiencing multiple steps of transformations in our IR module here. Okay, so in this lecture, we'll come back to the common theme of transformation. Just like we said, the key idea of MLC is trying to be able to represent the programs and be able to transform them in a flexible way. The fusion operations we introduced today is really primitive. So, for example, it's not as robust in some sense. For example, in a lot of fusion patterns, like in certain cases, we might get a fusion pattern like matrix multiplication that's followed by two addition operations. In this case, our current fusion path actually will create two parallel matrix multiplications that creates additional redundant computation, which is not desirable. A robust fusion pattern will detect this and try to avoid fusion in this case and only fuse and choose not to fuse, actually multiply to the add operation. Additionally, currently we are only using what we call pattern-based fusion, which means that we are detecting a specific pattern like dance and then add and fuse them together. A more robust fuser will try to analyze the patterns in a more generically. For example, it will analyze the addition and other operations by looking at the tensor IR functions and say, hey, is this pattern element-wise? Is this pattern broadcasting or reduction? And make use of those analyzed patterns to inform our fuser. And in this way, the fuser is much more generic, so you don't necessarily have to specify all the possible some instances of possible fusion patterns. We can do fusions like fuse all the element-wise operations onto complicated tensor contraction operations and so on. So these are more powerful optimization that fusers don't support. On the other hand, the lessons we learned today actually can be very useful. For example, in certain cases, if you want to go and customize the fusion behavior, for example, in certain accelerators, maybe you want to be able to fuse two dense operations together in a consecutive fashion. In other cases, maybe there are two consecutive convolutions that you want to fuse, while the original fuse is not necessarily ready to support it. So one thing you can do is you can go ahead and write a customized fuser that makes a fusion decision of taking the convolution operation, fuse them together. Of course, the customized fuser is going to be limited. Right? It's only going to fuse the particular instances of interest. But then what you can do is you can take that fused operation and run it through the generic fuser again, which will go ahead and fuse the rest of the component using original fusion patterns. And finally, this combination of two-step fusion will give you a more interesting fused patterns that not only leverages the original fusion patterns that our generic fuser have, but also have this new interesting behavior that you can go ahead and customize. And you can further explore what are the possible advances you can have by trying all those fusion patterns. So one key here is, again, compositionality. Right? All of those transformations are transformations among IR module towards IR module. And we want to be able to leverage the compositionality to allow us to compose different transformations together, like lowering to tensor IR functions with fusions. Sometimes we might want to lower part of computations onto libraries, then perform fusion and the tensor IR lowering on other parts. Really want to be able to organically compose them together so that it gives us a flexible way to optimize our machine learning programs. And that's kind of come back to our overall theme of MLC. Okay, so thanks for listening. This is the end of today's episode, and I will see you folks next week.